Hello, my name is Antoni Frej, and I am very pleased that I was allowed to present my recent study here at TMAG2021. Today, I would like to present all-optical magnetic recording with single L-band laser pulse in yttrium iron garnet with cobalt dopants. The research was performed in the group of Professor Stupakiewicz at the University of Bialystok in Poland with support of the Foundation for Polish Science. In the beginning, I'd like to briefly present main points of my speech. I'll start with short introduction of the all-optical switching of the magnetization, and then I'll introduce the studied yttrium iron garnet with few properties. Next, I'll present the laser-induced magnetization precession with obtained results and the results of the photomagnetic switching in the material. After discussion of the efficiency of the switching, I'll end with conclusions. The all-optical switching was first discovered in metals. One of the most important material is an alloy of gadolinium, iron and cobalt. This ferrimagnet allows for a magnetization reversal with single, short laser pulse, no matter what wavelength and polarization. The results can be seen on the screen. The two rows of the images represent two different magnetization states. For both of them, the magnetization switching can be obtained. The other important material is a multilayer ferromagnet with given composition. However, the switching in this material is a slow process based on the domain wall motion and requires multiple pulses, as can be seen in the picture. It also depends on the polarization of the light. What's more important, the switching in both materials is based on thermal demagnetization. Here, the distinguishing group of the materials are dielectrics. Recently shown all-optical magnetic recording in cobalt-doped yttrium iron garnet thin ferrimagnetic film is an ultra-fast effect based on the magnetization precession instead of the heating of the material, and the switching is both polarization and wavelength dependent. As can be seen, it requires only one pulse. For a better explanation, I'd like to present a few parameters of the studied material. A cobalt-doped yttrium iron garnet was grown with liquid phase epitaxy on gadolinium-gallium garnet with 4-degree miscut, a 7.5 micrometer layer. Two important for us crystal sublattices, tetrahedral and octahedral, can be seen in the picture. In them can be found the cobalt dopants in the previous locations of iron ions. The presence of cobalt is responsible for magnetic properties of the garnet. Here you can see the magnetic states in the material with domain structure in the bottom. Four different magnetic states can be distinguished, two major marked as M+ and M- along these two axes, and two minor along these two axes. The sample shows a strong cubic anisotropy. As you can see, the presence of cobalt ions in tetrahedral, marked as red, and octahedral, marked as blue, sublattices has major contribution to the sample magnetic properties. Due to this, the excitation of the electrons in the cobalt ions induces the additional magnetic anisotropy. The presence of the cobalt ions has also strong influence on the absorption of the garnet. Here you can see the absorption parameter for different wavelengths. In pure yttrium iron garnet, as marked as blue line, and in the one with cobalt dopants marked as black. We can say that the change in the absorption, clearly visible in the near-infrared range, results from the cobalt ions, for which a lot of the electron transition have been already identified, as can be seen on the left. For two of them, at 1300 nanometers and close to 1100 nanometers, the switching of the magnetization has also been discovered. Now we would like to know if it's also possible for the transition at 1590 nanometers. If we take a closer look at the absorption, we can see that it is significantly lower for this wavelength. If we also think about possible application of the phenomenon in data processing, this wavelength gets even more interesting because it lays in the range of the lowest attenuation of the optical fibers, as can be seen on the screen. The telecommunication L band is the second most popular band in the data transfer after band C. The switching in this range would give the possibility to easily exploit the phenomenon. The 1300 nanometer wavelength also fits in one of the bands, but with worse attenuation, so it's less interesting for this application. In order to investigate the possibility of the switching, we started with a study of the magnetization precession. Light-induced magnetization precession is well described with Landau-Lifshitz-Gilbert formalism. Using the pump probe method, one can observe the Z magnetization component by detection of the Faraday rotation of the probing beam. We have measured the precession in the wide pump wavelength range from 1150 up to 1600 nanometers. Thanks to this, we were able to find some possible changes in the signal. We have fitted the data with given formula, and then we plotted the amplitude and frequency parameters. Here you can see some changes in the frequency of the signal in comparison to other wavelengths. Here is the amplitude versus wavelength. Two maxima at 1300 and close to 1600 nanometers can be seen. They correspond to two electron transitions in cobalt ions and suggest better electron excitation efficiency. The frequency dependence also reveals changes at these wavelengths, with values far from ferromagnetic resonance mode. The increase in the amplitude, in fact, is an increase in the precession cone angle. This results in the increase of the dissipation of the energy that is also the damping parameter. Here you can see the relation between frequency and Gilbert damping. With increase of the damping, the frequency reduces. This result again points at the better electron excitation at wavelength close to the 1600 nanometers. Since we saw some changes in signal at this wavelength range, next we examined only 1590 nanometer wavelength in dependence on the polarity. One can see the change in the phase and amplitude for these four polarizations corresponding to crystallographic directions. The exchange of signal is smooth, and plotting again the amplitude parameter from fitting, we can see how similar it is to the data obtained for pumping at 1300 nanometers. Therefore, we assume that the excited ions lay in the tetrahedral sublattice as was predicted before. Having a specific wavelength and polarization, we can increase power and look for the magnetization switching. We observed the sample in polarized light and pumped it with single laser pulse. Here can be seen a switch domain obtained with single laser pulse with wavelength of 1590 nanometers. In order to assess its size and compare with other results, we subtracted the images from each other and calculated the ratio between the domain and the laser spot. Here are the results obtained for different pumping wavelengths, with previous results at 1300 nanometers and 1140 nanometers. The switching occurred for two different polarizations. And here are the results obtained for the wavelength around 1590 nanometers with polarization same to the one at 1300 nanometers and lying perfectly in the L band. These three maxima correspond to free electron transition in the yttrium iron garnet with cobalt. To estimate the efficiency of the magnetization switching, we measured the laser fluence dependence, and here you can see its effect on domain size. Plotting this with data for 1300 nanometers, we see that the threshold fluence for the switching at 1590 nanometers is almost twice as high as for 1300 nanometers. Also, the slope for 1590 nanometers is smaller than for the other wavelength. One can also observe the saturation of the switching at 1300 nanometers, not possible to observe at fluences needed for 1590 nanometers, due to the possible damage of the sample. For proper estimation of the efficiency, one has to take into consideration the absorption parameter, which is much smaller for L band. Calculating the heat load from simple equation, we can see that at 1590 nanometers, we lose much less energy, which results in the lowest dissipation. To conclude, we have obtained the all-optical magnetic recording with single laser pulse at 1590 nanometers with excitation of cobalt 2+ ions in tetrahedral sublattice and lowest heat dissipation. Such results opens a new way for application of the magnetization switching in the data transfer systems. With that, I would like to end and thank you for your attention.